have that assignment or that worksheet, please grab that. It looks like this. Let me turn it sideways so you can see it better. So this was classifying chemical reactions. This was the worksheet you had to do for the bonus point opportunity. I have the key to it. I'm actually just going to scroll down so that you can see what each one should have been. So if anybody has any questions on this in particular, we can look at a specific one. I know that I don't think on the key these are balanced just yet. So I'll actually just go ahead and say, does anybody have any questions or want to look at a particular one? Can you explain redox? There, I knew we'd have a question. Yes, I can. So I'm going to look at a couple of examples of these. You can see a lot of these are classified as redox and as something else. And that was part of the instructions. Let me scroll back up. You were instructed to, one, classify each reaction as acid-base redox, and you could also classify it as synthesis. Remember, another name for synthesis, though, is combination. And on the exam, I'll tell you whether I want you to say combination or synthesis, because Blackboard just will make me pick one when I write questions. So, and then decomposition, single, double, replacement, or combustion. And it says they may be more than one. And often you see, let me scroll back down, they are classified as more than one. So let's just look at this very first one right here, okay? This is a synthesis and it is a redox. Synthesis and redox, okay? So what's happening here? Well, one, you can see two things are coming together. Two compounds are coming together to form one thing. So that is why it's synthesis, or if you wrote combination, that's fine, I'll accept that. Okay, but how is it redox? So here's what I notice. When you do oxidation numbers, you always assign the positive oxidation number to the first element and the negative oxidation number to the second element. Okay, you assign the positive oxidation number to the first element in the compound, negative oxidation number to the second element. So if we're looking at this right here, NH3 and then HCl, and then we've got NH4Cl. One thing I'm going to do is I'm going to go ahead and assign what I know first. I know Cl is always a negative one, okay? Your main group 6 and 7 elements are usually always very predictable. And then over here, I know that Cl minus is also a negative one, okay? So chlorine is actually not what's being oxidized or reduced. It's either it's nitrogen and hydrogen. That's what's changing. I know that the hydrogen right here with chlorine, because remember rule number 4 on oxidation numbers was that the sum have to add up to 0. So right here, hydrogen is a +1. Okay, that's the oxidation for that hydrogen. Now, one thing you have to remember is that ammonia is a polyatomic ion, and I see a polyatomic ion right here on the product side. Okay, overall, ammonia has what charge? +1. Thank you, Brooklyn. So what that means is the sum of the oxidation numbers just within nitrogen and hydrogen, they have to add up this time to a +1 and not a 0 because it's a polyatomic with a charge on it. Okay, so I know this, the oxidation number on nitrogen plus the sum of the oxidation numbers on the hydrogens have to add up to +1. This is for ammonia, all right? And I know for hydrogen, it's going to be the oxidation number times 4. Okay, because there's 4 hydrogens within that, all right? So to add up to a +1, you've got nitrogen is going to be I believe on this side, hydrogen to be +1, we've got to have, this is a little bit, if we have a +1 here on the hydrogens, and we have a -3, that works out to +1, but this seems to break the rule that you put the negative first and the positive first and the negative next, okay? So that one is a little bizarre, that the nitrogen would be the negative and the hydrogen would be positive, but that makes sense because hydrogen usually is a +1, okay? So it must be that something bizarre is also happening over on this side with NH3. So these over here, the oxidation numbers have to add up to 0 because it's not a polyatomic, okay? So on this side, it has to add up to 0. So I think we have this just a bit backwards, actually. Sorry, I'm going to erase this. What has to be happening here is that you have a +5 on your nitrogen and a -1 on the hydrogens. Okay, so that's actually how you get the +1. Sorry. On this side, these add up to 0. So here hydrogen is a -1 and nitrogen is a +3. So there, I'm going to write these in, sorry. This one's really challenging. And we got -1 right there. Okay. So you can see a couple of things. You got hydrogens with 2 different oxidation numbers on this side, on the reactant side. You got a -1 and a +1. Why does it add up to 0? Can we go over oxidation reduction? Okay, so that has to go back to, if you slide over to the chemical reaction slide, let me answer this question really quick. When you assign oxidation numbers, we talked about the rules right here. Remember these rules for assigning oxidation numbers. Okay. Rule number 4 says the sum of oxidation numbers in a neutral compound is 0. So that's ammonia in this case. And NH4 is different because it's a polyatomic. All right. So this one's actually really, really hard. I'm probably not going to put one that hard on an exam. But you can see charges is changing. The nitrogen is going, I wrote +1, that should be a +5 right there. From a +3 to a +5. And then we have hydrogen changing from a +1 to a -1, this one right here. All the hydrogens are -1, and then this hydrogen in the HCl is a +1. Okay, so you got nitrogens being oxidized, hydrogens being reduced. That one's really, really, really challenging and really confusing. So let's look at an easier one, but you can classify that both as synthesis and redox, okay? A much, much easier one to tell that it's redox is zinc and sulfur make zinc sulfide, okay? You know from rule number 1 that any element by itself gets an oxidation number of 0. So it's very easy to come through on the reactant side and say, okay, zinc, sulfur, 0, 0. All right. Now on the product side, they're in a compound, so they have to have oxidation numbers. Again, positive oxidation number first, negative oxidation number second. So here sulfide, what is, anybody want to guess what the oxidation number on the sulfur is going to be in zinc sulfide? Rachel, I'll address that question in just a second. Let's finish this one real quick. Sulfide's going to have a, thank you, Brooklyn, a -2. It's main group 6. And usually elements in main group 6 have a -2 charge as an ion. So that means zinc's going to have a +2. So we can look at this very easily, see charges are changing. And if I don't ask you what's oxidized and what's reduced, then you can just label it from that point on. But if I ask you, okay, which element's being oxidized, which element's being reduced, make sure you specify. Okay, so zinc is being oxidized. It's going from 0 to +2. Sulfur is being reduced, going from 0 to -2. So Rachel's asking in the chat. So elements on the reactant side have their regular charge, and then on the product side is what charges, like what we calculate. Rachel, that's just if you have a polyatomic that there's particular charge. I mean, this one was really challenging because we had to look within the polyatomic and recognize things don't add up to 0 in that case. Normally, rule number 4, the sum of oxidation numbers in a compound add up to 0. So that's the only reason I was saying things have to add up to like a +1 over here for the nitrogen and the hydrogen. That one was particularly challenging because of that. I don't know if that answered your question though. On the reactant side, it's not that they have their regular charge necessarily. You just have to look. If they're by themselves, they're no charge. If they're within a compound, then that's where rules 2 and 3 apply for oxidation numbers. I'm going to slide back over to that lecture. Rules 2 and 3 tell you when to apply different oxidation numbers, usually ones that match their charges as an ion, okay? But then sometimes you run into some bizarre things where nitrogen's a +5 and not a -3 and stuff like that. Does that help at all, Rachel? Basically, you really have to pay attention to rules 2 and 3. You're not just, okay, I hope that helped. Anyway, so there's several of these. You can see that we're labeled redox, redox, redox. A lot of these charges are changing. Okay. So anyways, oh, I thought number 6 was very interesting. Did you guys see number 6? So number 6, you have aluminum and sulfur, and it's breaking down into aluminum element and sulfide as an element. And that's redox as well, because it's just kind of opposite of number 4. 4 and 6 are opposite. One's combination, the other one's decomposition. And so you have the compound on the reactant side. So that's where they're going to have oxidation numbers that are not 0. But on the product side, the oxidation numbers are 0. Okay. Bailey says in the chat, so what classifies something as a redox? Because one is being reduced to, right? Yeah, one is always being reduced and one's always being oxidized. You can't have oxidation and reduction without the other. There's going to be in tandem. Okay, something will always be oxidized and something will always be reduced. You won't just have one or the other. Basically, Bailey, the way we defined redox is we said charge is changing. You look for the change in charge. Okay. And that's how you know something is a redox. Something's giving away electrons or something's receiving electrons. Okay. Does that help explain, Bailey? You can always identify something as oxidized and something reduced based on the change in charge. So aluminum here, if we're looking at this, aluminum is always, we should know by now, is a +3. That's what we're going to give it. Sulfide here is the -2. And then there's 0 and 0. So you can see aluminum, is it being oxidized or reduced?
Reduced.
Yes, it's going from +3 to 0. Sulfide is going from -2 to 0, so it's being oxidized. Okay, so we can identify what's being oxidized, what's being reduced. That's why it's redox. So I hope that clarifies a little bit on the redox stuff. Are there any others? I will tell you another one that's really hard with the redox is combustion reactions. They are also redox, but when you get down in the weeds of that, it's very hard. That's why I didn't ask you on these what's being oxidized, what's being reduced. I just said, is it redox or not? Can you tell charge is changing? The key indicator here that a combustion reaction, this is combustion, is redox, is the fact that you have oxygen by itself. So you would give it oxidation number of 0 on the reactant side, but then you have it in 2 compounds. And it doesn't have an oxidation number of 0 in compounds. It's probably a -2 is usually what oxygen carries. So, and then I don't even know at this point, we'd have to really get into it to see, okay, oxygen's being reduced, what's being oxidized. And combustion reactions are really, really hard to tell in that sense, because you have this huge, look at that, you have this huge molecule. So anyways, on some of these, again, I'm not asking you what's oxidized or reduced. Can you tell its charge is changing somehow? And a key indicator is if an element's by itself on one side and then it's in a compound on the other side. Does that make sense? Does that kind of help simplify redox a little bit?
I have a question about like the first one we did.
Yes, Zoe?
Can you like scroll back a little bit?
Yeah.
Yeah.
Okay, one, I'm not going to put one this hard on the exam. I'm just going to tell you.
Okay, yeah, because I see if we know that it's redox, why we do it, but I mean, like, if I did not know it was redox, I would put like, I guess a hydrogen. Why is it a -1 and not like a +1?
Because it actually has gained an extra electron versus giving one away. We know hydrogen usually always gives one away. And I would love to make generalizations all the time in chemistry, but the more you study chemistry, the more you realize things behave in different ways based on what they're bonded with. And there are times where hydrogen here carries a -1 charge, and that's so bizarre. We're not used to that, okay? And the reasons why that happens and all of that is just, we're not going to dig into some of that. But that's the way it works out with this equation. And I know that's, again, there's usually exceptions the more you study chemistry. And I know that's really honestly probably a frustrating answer, but it's just the nature of it.
Okay, no, it's fine.
Does that help, Zoe?
Yeah.
It's a great question. But again, you assign the first element with the positive oxidation number, the second element with the negative oxidation number. So. Okay, any other questions on this? I'm going to post this key onto Blackboard so you can kind of dig through it a little bit more. And if you have any questions on any of these, I have an office hour from 9:30 to 10:30 today. I'm happy to like work any of these out. I know I haven't gone through and balanced these, But hopefully working through a couple of these with the redox was helpful. I'm trying to see if there's any that I thought were particularly challenging that I'd love to look at. I'll ask you guys this. What's the key indicator that you have a double displacement reaction? How can you look at a reaction and know without tracking what's changing and all that? Can anybody help us out with maybe a tip there? We had several on here that were double.
Like when something
Oh, Glenn?
is like in parentheses, I guess.
I would say like if there's both compounds on both sides, like if there's nothing alone on both sides normally.
Right. So it's not necessarily, Glenn, that you have like something in parentheses. It's you look at what your reactants are. If you have 2 ionic compounds on the reactant side, that's setting up for, that's double displacement. Okay. If you have 2 ionic compounds, you have a cation and an anion in each compound, then the only way those can react is for both things to switch. Both cations and both anions switch. Okay. So for example, number 9 here, I'm going to just highlight. I like to highlight the cations blue and the anions red. The cation is magnesium and hydrogen. The anion is the hydroxide and the sulfate. And then you can see on the other side, you got a red and a blue piece on each side as well there. You got cations and anions on both sides, okay? So that's why we classified it as double displacement. Number 10 is the same way. So, and then what's the key indicator that you have a combustion reaction? Anybody? What's the key sign?
Water.
Yeah, you form water and CO2. Okay, water and CO2. So were there no precipitate reactions? Whitney, that's correct. You're looking through it and say, I thought there were precipitate reactions. I don't see any on here. I'm pretty sure, hold on, did the instructions say, you know what? The instructions did not even say classified as precipitate reactions. So did you guys see one that was a precipitate? That's actually a great question. Maybe it didn't have precipitation on here. There may have been one I'm thinking of, like number 10 right here, copper and hydroxide. When I look at the solubility chart right here, neither copper nor hydroxide is on the solubility chart. So we go back to that sheet. This element or this compound right here, this would form a precipitate, right? Because neither copper nor hydroxide are on the solubility chart. So that's not going to be soluble. Is that the one you got as precipitate? Okay, good. And so you could indicate this as an S right here. It's going to form a solid. So it's not only double displacement, it's also precipitation. Were there any others that y'all recognize as a precipitation reaction? Off the top of my head, that's the only one that oh, right here. Barium sulfate is an exception. Okay, so barium sulfate would form a solid. So this is not only double displacement, this was also precipitation. Thanks for pointing that out, Whitney. So there we go. That's a few that I just noticed. What is the definition in the chat? What is the definition of precipitation again? It is 2 aqueous reactants creating at least one solid, right? That's correct, Rachel. 2 aqueous reactants, and then one of your products is a solid. Okay. Now again, none of these have the little abbreviations that we're writing in. And so I may give you a reaction that doesn't have anything labeled as aqueous or liquid or solid. If I do, that's a key indicator. Oh, if I have a solid on my product side, that's a precipitation reaction. But if I don't label any of them, it's probably because I'm wanting you to go through and label them or use the solubility chart to determine if one of your products would be solid or not. Any questions on how to use the solubility chart? The solubility chart will be on your resources page for exam 2. Okay. All right, so this was a challenging exercise, but I hope it makes you feel more confident at least on classifications. There's not going to be 15 or 20 classifications on the exam. Just a couple, okay? Any other questions on this? All right, well, I want to jump over to, again, I'm going to post the key for this on Blackboard if you want to dig through it a little further. But I'm going to jump over here to, this is our mole mass relationship slide. This is kind of where we ended the other day, talking about mole ratios and working the problem with rust and with iron. And we're going to pick up here and we're going to do some review. One problem that I actually wanted to spend some time working is right here. So if you joined us for lab, which by the way, I've kind of noticed attendance, some people have emailed me, so if you're one of those people, disregard, but I just want to encourage you guys to be diligent to attend labs. I'm thankful even for students that are say, hey, I have an appointment or I have something during my normal lab time. Can I join another lab? And I've always said yes to that, okay? Because I think it's important that you're there. So please make every effort to attend your lab times. I think if you talk to students that do regularly attend, I know lab's not a perfect setup. I know lecture's not a perfect setup. I know there's things frustrating about this class that you probably wish were different, and I get that. It's not perfect setup for me either, but I think overall, hopefully students would say that they're helpful to some degree, to have other people to check with and talk to, even if your lab group doesn't talk a whole lot. Hopefully, at least to some degree, it is helpful, even to have me there and flag me over and ask me questions. So please, please, I beg you, come attend labs and make an effort to be there. They're helpful. If not, you got to do the lab all on your own, and that's really challenging. So Kylie says, how many questions will be on this exam? Very similar to last time. You're going to have around 10 to 12 multiple choice. Whitney says, we don't have lab at all this week. So the Monday people finished up the mole calculations lab yesterday, but correct. Thursday and Friday people, because of the exam and because we have not covered any new content, all we've finished is chapter 6. We don't have any lab material to do for this week, okay? So we're gonna have lab next week on chapter 7 stuff, but Thursday, Friday people, no lab this week, okay? So anyways, going back to talking about labs, we did a lot of problems that were the 3-part problems. And I think it would be helpful to work another one together because those are the most challenging. So that's what this one is. I'm going to erase here. I was working a problem yesterday in a Zoom with some students that had some questions. It was a really great, great hour we spent working on some stuff. But let's read this problem and work this out. This is a 3-step problem. And there's actually 2 questions in this problem. We'll probably just do part 1. All right. So this says you need to make 100 grams of calcium oxalate. What is oxalate? Well, we have a picture of it right down here. It's 2 carbons with 4 oxygens. You can see how they're bonded. And then the dotted lines indicate resonance. Okay, if you're wondering why are there dotted lines? Resonance is not something we've talked about. Electrons can move around and bonds can slightly change. So that's what the dotted lines indicate. But don't worry about that. Basically, it's C2O4 with a -2 charge. Okay, we'll write that out in a minute. So it says this, you need to make 100 grams of calcium oxalate. Calcium chloride mixed with sodium oxalate react, so those are your reactants, and those react to make your products, calcium oxalate and sodium chloride. So it's a double displacement reaction. How many grams of sodium oxalate, and here's the second question, how many grams of calcium chloride do you need? Again, we'll probably just answer one of those questions because you work on both the exact same way, okay? So calcium oxalate, that's one of our products. Calcium chloride mixed with sodium oxalate, these are our, I'm gonna put an R for reactants. These are our reactants. And then calcium oxalate and sodium chloride, these are our products. So let's write a balanced chemical reaction first off. A balanced chemical reaction. Here's what I noticed. We've got grams of calcium oxalate given, and then it says how many grams of sodium oxalate. So this is a mass of substance A to mass of substance B problem. This is a 3-part problem. If you remember from the diagram, this is how we're going to work it. When you are given the mass of A and you're asked for the mass of B, you use both. Both what? Both a mole ratio and molar masses. And that's what we're going to do. You're going to need calculators, by the way. Grab one if you don't have it. So let's write out calcium chloride. Somebody tell me the formula for calcium chloride. I don't understand how to use that slide, the one with the arrows. Okay, thanks, Bailey. Okay, Kylie, that's calcium oxalate that you gave us, which is great because we're going to need that as well. Brooklyn gave us calcium chloride. Bailey, we're going to walk through that diagram as we work this problem. Okay, so hopefully maybe by the end of this problem that will help. All right, so calcium chloride, CaCl2, and then sodium oxalate. Sodium oxalate, so sodium is Na. We know it has a +1 charge. Oxalate is over here. Oxalate is the C2. There's 2 carbons. There's 4 oxygens, and it's got a -2 charge. So that's just how we'll write it. So if we've got a -2 charge and then sodium has a +1 charge, we're going to need 2 sodiums. So it should be Na2 and then oxalate, C2O4. So these are our 2 reactants. And then these react to give us calcium oxalate, which Kylie typed in the chat for us. Calcium oxalate is CaC2O4, CaC2O4, and sodium chloride. So then sodium chloride should be NaCl. Okay, questions on how we just wrote this out? Now we need to balance it, right? So y'all look at this and put coefficients in. What coefficient should we have for the balanced chemical reaction?
Wait, so like, is that like the second half of the equation? Like,
No,
after the arrow?
no. What do you mean, Glenn, over here? Yeah, these are
Yeah.
your products, and then before the arrow, these are your 2 reactants. The calcium chloride and the sodium oxalate are your reactants. And then the calcium oxalate and the sodium chloride were the 2 products. And I got that from this second sentence. I'm going to highlight it in yellow where it says this right here. I pulled all what we just wrote, I pulled out of that whole second sentence.
2 in front of sodium chloride.
Okay.
Okay, Christian says a 2. Does that help, Glenn?
Yes.
If it doesn't, let me know. Kristen said a 2 in front of sodium chloride. Is that it? And it's done? 1 calcium on each side. Remember, you can always do this. Take inventory. C2O4. I've got it on both sides. We're going to treat it as an ion. And then sodium and then chloride. And you can always take inventory. 1 and 1, double check. On the reactant and product side for oxalate, I've got 1 and 1. Sodiums now, because we put the coefficient of 2 on the product side, I've got 2 and 2. And then the chlorides, I had 2 on the reactant side, and now the coefficient gives me 2 on the product side. Okay, you can always do that to double check. Okay, now the question we're going to answer, I'm going to highlight it in blue. How many grams of sodium oxalate? Which one is sodium oxalate? That's our reactant. Okay, that is this one right here. So how many grams of sodium oxalate do you need to make 100 grams of calcium oxalate? Okay, so the 2 that we're interested in for this first question are the 2 highlighted in blue right there. We are starting out with 100 grams of this guy, and we want to know how many grams of sodium oxalate do we need to make that product, 100 grams of it. So because we're starting with the number for calcium oxalate, you could call this substance A. All right, so that's where we're starting with the mass of substance A, calcium oxalate. Because we're looking for the sodium oxalate, we could call this substance B. So going back to the diagram, Bailey had a question about this. I'm sure many others do as well. Here it is right here. We're starting with 100 grams of the calcium oxalate. We're looking for the grams of the sodium oxalate. So let me erase all my scribbles. This is how you use this chart. It's a 3-step problem. The first thing we're going to do, step number 1, is we are going to use the molar mass. You always, step 1, use the molar mass of substance A. So for that, it's going to be calcium C2O4 calcium oxalate. So we're going to use the molar mass of calcium oxalate, and we're going to use that to convert from mass is grams, right? That's units of grams, grams to moles. That's what this arrow indicates right here. We're going to convert from grams to moles. So always, step 1 is use the molar mass of substance A. once you have moles of calcium oxalate, step 2, always step 2 is the mole ratio. Okay, so we're going to use a mole ratio between what? Calcium oxalate and sodium oxalate. Those are the two things we're using in this problem. So between substances A and B. You don't have to label them A and B if that confuses you. You can just use the substances' names. All right, once we have, so substance B for us this time was the sodium oxalate. So once we have the moles of substance B, step 3 is you're going to use the molar mass here of sodium oxalate, which is the substance B, Na2C2O4, okay? And we're going to convert to the mass of, which is grams. That's what the question says. How many grams of sodium oxalate would you need to make 100 grams? So that's how you use the diagram. Bailey, does that help at all? And then we'll see how that plays out so far. Okay, so the method is the same. Obviously, the substances are going to be different depending on what reaction you're talking about, but the methods are the same. Always molar mass of the first thing, then a mole to mole ratio, then molar mass of the second thing. Okay, those 3 things never change. You just may have a different chemical reaction. Okay, so let's do that. So we have 100 grams of CaC2O4. And then we are going to use the molar mass of calcium oxalate. But guess what? We don't have the molar mass of calcium oxalate. We've got to calculate it. Okay, so we're going to plug in the molar mass, but first let's calculate it. I have calcium, I have carbon, and I have oxygen in this compound. I have 1 calcium, I have 2 carbons, and I have 4 oxygens. So can somebody tell me the numbers that we should type for these things? Calcium, we'll go to the periodic table. I think I might have one right down here at the bottom of this lecture. There it is. So you're going to find calcium, zoom in. I noticed that it's 40.078. And then we'll plug that in for calcium. Carbon is the 12.011. And then oxygen, I'd just like to use 16.0. So multiply those numbers from the periodic table by how many atoms you have of that element in your compound. Okay, and then if somebody wants to add all this up for me, you should have 40.078, 24.022, and 64.0. So what's the sum total? Rachel got 128.06. So that's how many grams of calcium oxalate per 1 mole. So now this is the molar mass. We're going to plug this in. I want grams to cancel. So I'm going to put the 128.06 grams on bottom. And this is C2 or CaC2O4. And that's per 1 mole. And I like to write in the substance CaC2O4 so that I see when I go plug in my molar mass next, I don't mix this up, and that I get the right moles on top and right moles on bottom for my substances. I need to, the next step, so this is going to be step number 2. So this was step number 1. Step number 2 is you plug in a mole ratio between your 2 compounds. So what is our mole ratio between our 2 compounds highlighted in blue? Rachel says 2 to 1. Look at the coefficients. Yeah, that's correct, Maria, Kylie, 1 to 1. So Rachel, we got a coefficient of 1 here. It's an understood 1, right? We don't write the 1s in a lot of times. So I'm going to write for every 1 mole, and just because it's a 1 to 1 mole ratio, obviously multiplying and dividing by 1 is not going to change your answer. But what really matters here is the units. We have units of moles of one thing. We've got to convert to moles of the other thing. So for every 1 mole of calcium oxalate, it's 1 mole of sodium oxalate. Okay, and then the next thing we have to do, what is that? So that's step number 2. And you see that moles of calcium oxalate are going to cancel. Anybody for step number 3, we've got to then plug in the molar mass of our other thing, which is sodium oxalate here. So we've got to also calculate the molar mass of sodium oxalate. So I'm going to jump back over to the periodic table to get the number for sodium, which is 22.99. If you use 23.0, your answer will still be counted correct. So let's just use 23.0 on sodium. Calcium and oxygen, or sorry, carbon and oxygen are still going to be the same. So the molar mass for sodium oxalate should just be, I've got sodium and I've got 2 of those. So let's say times 23.0. Carbon, 2 times the 12.011. And oxygen, 4 times the 16. Okay, so we'll say 46. And then 24.022. And then 64. And then total, anybody have the total for us?
Dr. Eberly.
Yes.
So we're finding on the mole to mole ratio, we're using those two because that's what we want to figure out how many grams there are of, correct?
Right. So the question up here, the one I highlighted in blue from the word problem, that's the part we're answering right now. It says how many grams of sodium oxalate? And we're starting with the other part that I'm going to highlight in blue. Well, that's the pencil. 100 grams of calcium oxalate. So the reason we picked the mole to mole ratio between calcium oxalate and sodium oxalate, Blake, was because from the question, we're starting with the calcium oxalate and we're answering the question, how many grams of the sodium oxalate? So that's why we're looking at the mole to mole ratio specifically for those 2 things. Does that help?
Yes, ma'am.
Thank you for interrupting me and asking that. Is it okay? Okay, so 134.022 looks like, okay, Bradley says that as well. All right, 134.022 grams of the sodium oxalate, and that's I'm gonna squeeze it in per 1 mole. So this is our last step. This is step number 3 from that diagram. This was step number 2. And step number 3 is we're plugging in this molar mass for sodium oxalate. And I want moles to cancel because I want to end up with grams. So I've got to put 1 mole on bottom of the sodium oxalate. And then it's 134.022 grams. So then you can see grams of calcium oxalate cancel, moles of calcium oxalate cancel, moles of sodium oxalate cancel. You're left with grams of the sodium oxalate. So now we do all the math. 100 divided by 128.06 times 1 divided by 1, but you can, in your calculator, you don't have to put that in, times 134.022. And what's our answer going to be? Brooklyn, is that the 104.66 final answer? The grams of sodium oxalate? Okay, so Brooklyn got 104.66 grams of Na2C2O4. Okay, so now you see why I say the 3-part problems are the hardest things. There's so many steps. This one was huge because you had to not only write out the equation and balance it, then you had to calculate the molar masses of both things and then plug it all into the problem correctly, okay? Questions on this? Hopefully with me labeling the steps 1, 2, and 3, and I'm going to scroll up for just a second, but I'll be back. That corresponds to the steps 1, 2, and 3 on the diagram. So anybody who still finds the diagram confusing, can you help me maybe understand what is it that throws you off with the diagram? Just like, I want to know maybe how I could better explain it, but I'm sure that's a hard question because if you're confused, you're just not sure maybe what it is.
Like for mole, A. So like, are we always supposed to write the ratio there? Like, is that like guaranteed?
Yeah, step number 2, the 2 with the circle around it, always corresponds to plugging in a mole to mole ratio between your first compound and your second compound. Like the compound you're starting with and then the compound that the question's asking about. Okay,
Will
good.
there just be one of these that we will need to work out completely for the exam?
This is a great question, Kristen. Yeah, I guarantee you the file response question that I give you for the exam, there's actually going to be 2 file response questions on exam 2. One will be drawing Lewis structures from Lewis structures and condensed structures. I'll probably have a couple, 2 or 3 you got to draw. That'll be one file response question. The other file response question, no surprises. It's going to be a 3-part problem. Okay. So. And it'll probably be worth a lot of points because they're a lot of work. But again, I want you to know I give partial credit on file response. If you get 90% of it right and you just get the wrong answer or something like that, you're going to get 90% of the points. Okay, but please use units and please clearly label stuff. That will help me give you points. Rachel says, will we draw it on paper and then submit it? The Lewis dot structures? Yeah. So have some paper that you can draw on for the exam. Your Lewis structures and do the file response question. Okay. All right. Now to look at a few, well, let's see, we get done at 9:15, so we got about 30 minutes. So we're going to work through some of these review questions, and then we need to save at least 20 minutes at the end. So in about 10 minutes, we need to switch over to Kahoot. And I'm sure y'all want that bonus opportunity. So let's look at these. Review. This is some chapter 4 stuff. Okay, it goes all the way back to covalent compounds. Hold on, Whitney has a question. If we have trouble submitting it, is it okay we email it to you? Yes, always. If you have trouble, any questions like I don't know if that's submitted correctly on the exam, please just email it to me, label it as exam 2 file response. Okay, molecular compounds. So by the way, actually, before we jump into this, I want you guys to, I'll take 1 minute, maybe a minute and a half. Write down 10 things, 10 topics that you think are going to be on exam 2. Grab a sheet of paper. 10 topics from across chapters 4, 5, and 6 that you think are going to be on exam 2. Let me find I don't know if I have a blank slide. I can get one. Rachel, will molecular geometry be on the test? Yes, it will. I'm going to try to hit that on some review. We're going to spend some review mostly looking at chapters 4 and 5 stuff because we've done a lot of chapter 6 stuff more recently. Yes, it will be though. And I'll have that, I'll probably put that table, the molecular geometry table, on your resources page. All right, take about 20 more seconds. You may not have gotten to 10 and that's okay. I bet together we'll get 10. All right, I've got a blank slide here and let's see how many we can get. So let's start with chapter 4. Anybody remember concepts from chapter 4? This was covalent bonds. What else did we have from chapter 4? Molecular geometry was one Rachel mentioned.
Lewis structures.
Lewis structures. Whitney says, when will the resources page be available to us? Probably by the end of the day tomorrow. So that way you can look at it either tomorrow evening and Wednesday and see what's on there. Binary compounds, naming binary compounds. Good. Knowing diatomic molecules. Okay. Polar bonds. And polar molecules. Chapter 4 is huge. A lot of big things. Okay, chapter 5. We had balancing reactions. And classifying. We learned a lot of ways. These were really the two big things. There's a lot of details under classifying, right? You have like 5 different ways we talked about, the single or double displacement. And then we had the acid base, precipitation, and redox, but that's all under the umbrella of classifying chemical reactions. So that's really the main 2 hitters from chapter 5. Chapter 6. What all did we have there? We had, yep, moles. Okay, we talked about what a mole is, and we talked about Avogadro's number. We learned how to calculate molar mass. And we talked about mole ratios, how to write those. And then Rachel has a question in the chat for the last 3 acid-base precipitation redox. We learned it can only ever be one of them, right? Like precipitation can't be redox or acid-base at the same time. That's correct. I'm not going to give you a problem. That is both a precipitation reaction and an acid-base reaction, or and a redox reaction. So you'll just classify it one of the ways. Riley, can you scroll up? Yes, I can. So hopefully that helps you kind of divide into the different topics and maybe spend time making sure you know each of these different topics. One more thing I want to add to chapter 6 is just put those 3-part problems. That's okay. We learned how to use molar mass and molar ratios to do conversion problems. Okay, so wow, we are running short on time. I'm gonna go back to is everybody good with this? Can I go back to the other slides? Okay, let's go back to these review slides and spend the next few minutes doing this, and then we're gonna get on to Kahoot. So a couple of things. This is chapter 4 stuff. Molecular compounds, covalently bonded compounds. Usually form between, what do y'all think, A, B, or C? 2 metals, 2 nonmetals, or a metal and a nonmetal? You can just circle one on your page. And type it in the chat. What do you think, A, B, or C? Maria and Rachel say B. Anybody else? Yep, it's B, 2 nonmetals, okay? So remember that. Here's a question. Element X has 5 valence electrons. How many bonds will it form in a Lewis structure? What rule did we write down in class to use for questions like this? How many bonds? If something has 5 valence, nitrogen. Nitrogen's an element with 5 valence electrons. How many bonds would it form?
3.
3. Yep, that's correct. So it will form 3 bonds. There was a little rule that said the number of electrons it needs to get an octet equals the number of bonds it forms in a compound. The number of electrons it needs to get an octet equals the number of bonds it forms in a compound. Okay. I know I'm moving probably a little fast through this. Which of the following is or are not diatomic molecules in nature? sulfur, oxygen, fluorine, phosphorus, hydrogen. There might be more than one correct answer here. Okay, Gabby says D. I meant to highlight that. Whoops. Okay, so D. Rachel says A and D. So far we've got votes for this. That is correct. Okay, sulfur is not a diatomic naturally, and neither is phosphorus. So make sure you know which ones are. Oxygen, fluorine, and hydrogen definitely are. Name 3 elements that are exceptions to the octet rule. I want to skip over this. I'm not going to put that on the exam, which ones are exceptions, okay? All right, let's draw one Lewis structure, and then we'll do this question in the next, because the next one's a molecular geometry, and I think that would be a good review. But then we're going to jump over to Kahoot. Okay, let's do number 2. That one looks hard, right? So draw a Lewis structure for number 2 here. And then there's plenty of more to practice if you want more practice on these. I also sent out that list of recommended textbook problems, so you can practice those as well. All right, here's what I see. I've got carbon and I've got hydroxide in parentheses. So it means this hydroxide group is branched off of carbon. So I'm going to go ahead and, it doesn't matter if you draw it up or down, but it should look like this. Okay, it cannot look like this. It's the hydroxide group, one group. So the oxygen and the hydrogen have to be bonded together. All right, then I've got this carbon bonded to my next carbon. Remember, you can block it off in groups, put boxes around your groups if you want. So then I'm going to draw a hydrogen, or I say a carbon-carbon bond, and then that second carbon has 2 hydrogens branched off of it. Then this second carbon is bonded to the third carbon, and I've got a, hold on just a second. Something is bad wrong with that first carbon. We're supposed to have a CH3 group branched off of this. Okay, let me fix this. This might be a very bad example. Don't you love it when that happens? And then we should have a nitrogen and a hydrogen branched off of that nitrogen. Okay, this is wrong on many levels. So now the question has become, what's not the structure? What's wrong with the structure?
The first carbon should have 4 bonds, not 3.
Yes. Oh my gosh. I did not look over these very closely. I wrote these last semester. Okay, this first carbon only has 2 bonds. That's wrong. So that's not good. And then look at this third carbon. 3 bonds as well. You gotta have a lone pair on the nitrogen, by the way. And then this nitrogen is used to have 3 bonds. So maybe that should be a 2. So yeah, this is a bad example. Let's pretend that if these hydrogens don't exist, I think we can make it work. I will make sure I look over the structures very carefully for the exam. And then you could have something like that. But then this third carbon is still, we'd have to have another hydrogen in the structure here. This is terrible, guys. I'm very sorry. If you had a hydrogen written right here, and it would look like that. Well, oh, last thing, Lewis or lone pairs on that oxygen. All right, I don't know if that helped you or just confused you more. Let's move on to geometry, okay? This one should be written correctly. Which of the following molecules would have a trigonal planar molecular geometry? Trigonal planar molecular geometry. So this is really, it's been a while since we've done molecular geometry. Trigonal planar. So trigonal planar is 3 charge clouds. Remember how you count charge clouds? Bonds, single, double, and triple bonds count as a charge cloud. So it'll be helpful to probably draw out the Lewis structures for these. So if we're looking at the first one, it's carbon with 4 bromines. All these bromines should have, all their lone pairs on here. So carbon is definitely tetrahedral there. not trigonal planar, right? Because you got 4 bonds, which is 4 charge clouds. Bromine, BF3, you got, sorry, boron, BF3. Br is bromine, B is here is just boron. And you got your lone pairs on these fluorines. But remember, you don't count lone pairs on the perimeter atoms. You only count lone pairs as a charge cloud if it's on your central atom. So here, this boron just has three bonds. So this is 3 charge clouds, okay? There's 1 bond, 2 bond, 3 bonds. So that's 3 charge clouds, no lone pairs. And so that would be trigonal planar. I see that, so oxygen with 2 fluorines, that's gonna look like this. And then you got 4 charge clouds on that oxygen, 2 bonds and 2 lone pairs. 2 bonds and 2 lone pairs. So that one would be bent, this one would be bent, not trigonal planar. PCl3 looks very similar to BF3, but it's not trigonal planar. Why is that? Can anybody tell me why? You should have a lone pair on this phosphorus right here because it's in main group 5. So this one's actually pyramidal. 4 charge clouds, 3 bonds, and a lone pair means 4 charge clouds. So this one's actually pyramidal. And then ASF5 is 1, 2, 3, 4. You got 5 fluorines here. These should all have lone pairs, but that is definitely not trigonal planar. Abby says, if I go back into mastering chemistry assignments for extra practice, will it mess up my grades for any reason? No, it will not, Abby. It should not do that. Your first grade counted. So that's definitely fine for extra practice. Okay, so that's a little bit of the review. There were more review slides that I had here, but Kahoot is also going to be review on some of this stuff, polar bonds and polar molecules. So you can work through that stuff. Send me any emails with any questions you have. But I'm going to stop sharing. We have about 14 minutes left, so hopefully we can get through a game of Kahoot. So here's, and you obviously have a computer or cell phone if you're on Zoom. So what you're about to do is go to kahoot.it, and I am going to launch the game. And what I'm going to do is share hold on, it's loading. Okay, loading the game pin. Go to kahoot.it. Kahoot is K-A-H-O-O-T. Let me share my screen. And I think you could all see the game pin. Can y'all hear the music? Okay, you see the game pin? 639063. So you go to join at www.kahoot.it and put in the game pin 639. It'll prompt you for a game pin 0603. This is cool. I've never done like an online Kahoot version. This music is kind of annoying. So we have how many people? So we have 52 participants. So we're at 33 right now, 34, 35. $37. I'm gonna wait till we get up to close to 52. Anybody else gonna join? $41 now. So these questions will be timed. Grab a calculator. Make sure you have a periodic table close by, because that's all gonna help. Some of these questions you'll have like 10 or 20 seconds because there's no math or anything involved. Some of these questions you'll have more time. And we'll see how many questions we can get through. And then we'll see who's in first place when we do that, or if we have to stop early. Okay, we're at 44 and nobody else seems to be joining. Anybody else want to join? 43. Just type in the chat or unmute yourself if I need to wait. I don't see the. All right, I'm gonna go ahead and call it and start the game. All right, here we go. Okay, so hopefully you'll see the question on the screen here. Which element does not naturally exist as a diatomic molecule? So get your answer in. Fluorine, hydrogen, phosphorus. This is quick. 3, 2. Was that too fast? That was really fast. Okay. So the correct answer there, was, sorry, I've got all these, like the chat and everything. Phosphorus. Okay, phosphorus is not a diatomic. That maybe should have helped because we actually just went over that. All right, so next. Oh, it's going to show us who all's in the lead every time. Good job, Grant. Quiz 2. Predict one product from the double displacement reaction between the following two reactants. Okay, how much time do you have? You got like a minute and a half. So predict one product from a double displacement reaction between nickel phosphate, nickel 2 phosphate, and aluminum sulfide. Just one product is all. So this looks like, well, obviously it's double displacement. Your cations and anions are going to switch places. So we still have almost a minute left, but 36 already people have gotten their answers in. I wonder if I can like turn the music off there. That's probably helpful. All right, still got 30 seconds. I think we got most everybody. There's like 42 people in the game. Okay, I'm gonna move on so we can get to the next question. All right, I think 42, there we go. Yeah, nickel sulfide was the correct answer. Only 9 people chose that. Most people chose, let me see, most people chose Ni2S3, okay, but why is that wrong? Nickel here in nickel phosphate has a +2 charge, okay? If you really dig in and look at the charges, phosphate is a -3, and nickel, you've got 3 of those cations. So if you've got 2 phosphates, that adds up to -6, okay? So that means the cations have to add up to +6. So you've got 3 nickels, and it's got to add up to +6. Each one carries a +2 charge. Sulfur as an anion has a -2 charge. All right, so that's why NiS is correct. You got a +2 and a -2, so you just need 1 each on the product side. All right, this is totally an example of a question I would throw on the exam because I expect you to know how to determine cation and anion charges. Any questions on that one? Don't rush yourself on that one. You had a whole minute and a half. So I know it feels like you've got to rush on these. Sometimes you have more time. All right, let's see. We'll go to the next one. Okay. Next. What is the mole-to-mole ratio for silicon tetrachloride, SiCl4, and HCl in the following reaction? So you're looking between SiCl4 and HCl, you're looking at the coefficients, right? You got 20 seconds left. Is it a 1-to-1, 1-to-2, 2-to-4, or 1-to-4? Nine, 8, 7, 6. So this one, you're just looking at the coefficients. That one should have been, you should have been able to answer that a little more quickly. 1-to-4, you got a coefficient of 1 right here and a 4 in front of HCl, so it's a 1-to-4. And you can't simplify that because of the 1. Okay. Next. Which of the following is a precipitation reaction? Okay. So The reason you only have 30 seconds here is because you should just look at the abbreviations. And you're looking for a reaction that has an abbreviation of what on the product side. If it's a precipitation reaction, it forms a solid. So which reaction has a solid on the product side? You should be able, 3, 2, get your answers in. All right, the first one, that was the only one, this copper sulfide right here forms a solid. None of the others, liquid, aqueous, gas, liquid, and aqueous. So again, that one was a little easier because I put the abbreviations on there for you. And most everybody picked that first one, good. Okay, next. In this redox reaction, what is oxidized and what is reduced? Chlorine and sodium bromide. This is a single displacement reaction. I give you a minute and a half on this, so take your time. But you do get points based on how quickly you put your answers in. What is oxidized? What is reduced? So we got chlorine by itself on the reactant side. It displaces bromine. So in the product side, bromine is by itself, and then chlorine is with the sodium. All right, most everybody, 2 people left. Last person, get your answer in, there we go. All right, the correct answer was that bromine is oxidized. Why? Because right here on the product side, sodium bromide, it's a -1. On the product side, it's a 0. So it's going from -1 to 0, bromine is. So it's increasing in charge, which means it's giving away an electron to do that. So it's oxidized, bromine's oxidized. Chlorine is by itself, so it's 0. On the product side, it's a -1 over here. That's the oxidation number, you should have gotten it. So 0 to -1 is reduced. Okay, a lot of people pick the opposite thing there, that chlorine was oxidized and bromine was reduced. But remember, oil rig will help you keep that straight. Oxidation is the loss of electrons, charge is increasing, reduction is the gain, charge is decreasing or reducing. Okay, I want to see some people get in there and take first and second place. Dethrone Kylie and Grant. Okay, draw the Lewis structure for the following molecule. Name the geometry of the second carbon. You got a whole minute to do this. You got CH3, and then you got a carbon. This oxygen is branched off of this carbon. And think about how many bonds you need to draw between that carbon and oxygen. And then you got an OH group. Yeah, I thought you were in French class. All right, we got how much time? 20 seconds. So you get a CH3 group and then a carbon with an oxygen branched off it and an OH group. Get your answers in. Okay, the correct answer here was trigonal planar. So I actually just drew this on a sticky note real quick. And you should have something, let me see if you can see this. You should have something that looked like this, okay? So if it looked like this, you notice that second carbon has a double bond to the oxygen and then another single bond to an oxygen, a single bond to carbon. So that's 3 charge clouds, no lone pairs. 3 charge clouds, no lone pairs. I'm sure this is probably hard to remember if you're not looking at the chart, but that is trigonal planar, okay? 3 charge clouds, no lone pairs, trigonal planar, okay? Okay, next. We got 2 minutes left. Name the following binary compounds. So we're probably not going to get done. P2O5, This is where you had to use prefixes. So what's the prefix for 2? And what's the prefix for 5 on the oxygen? So it'll be something phosphorus, something oxide. Five, 4, 3, get your answers in. So the correct answer there is diphosphorus pentoxide. Okay, diphosphorus. So the blue one's not correct because diphosphide 1, the phosphide is not a thing. You don't change the name ending of the first element to IDE. And then the pentaoxide, remember you take the A out, it's just pentoxide. So that one's kind of tricky, but diphosphorus pentoxide is the correct answer. Okay, next. We got like 1 minute left, so we're probably not gonna get done. We'll see how far we can get. Okay, which of the following bonds is nonpolar? This should be pretty quick. You don't even have to use an electronegativity chart for this. There should be one blaring out at you that's nonpolar. 4, 3, 2. So thank you, good. Carbon, carbon. Anytime you have 2 identical elements in a bond, the electronegativity difference is going to be 0. So when you have a bond between 2 identical elements, that one is always nonpolar. So that's the carbon-carbon bond there. All right, this is gonna be the last question we do because it's 9:15. You got time for one more? Which of the following molecules is polar? Consider the Lewis structure on this. Which molecule is, which molecule is polar? So remember, if a molecule is 2 identical elements, is that polar or nonpolar? If it's ionic, we don't consider it polar because it's ionic. So there should be one. We've looked at it a couple of times in lecture. Okay, that one was quick, I know. You didn't maybe have time to draw all the Lewis structures, but CH3Cl is polar. The carbon-hydrogen bonds are not the polar part, but that chlorine is very electronegative because it's an element right next to fluorine. So that one is polar. So, all right, this is probably all we're gonna have time for. So I'm gonna write this down. I know we didn't get through all the questions, but I hope this was at least fun playing. Kylie, Chris, and Grant. Shoot me an email, Kylie, Chris, and Grant, and you guys will get a few extra bonus points, opportunity to add to whatever assignment you want. I'm gonna give first place 4 bonus points, second place 3 bonus points, third place 2 bonus points, okay, to add to any assignment. It could be your exam or whatever. So shoot me an email, you 3. Other than that, I'm sorry we went over on time.